Hello, let me start my presentation. And in my presentation is consisting of the five question from A question to the E question. So I will go through them together. And my problem is mainly deal with this xt function, which consists of the three different frequency, like this and this and this. And the first question is what is the high frequency in XT? We can just confidently say we can just surely say this is the highest, and based on Nyquist criterion, I mean what is the minimum reconstruction minimum sampling rate required to reconstruct this continuous signal. Then at least we all know we need twice times higher than the highest frequency. So this answer is natural. And second question is simulate the downsampling process without any filtering by extracting every 20th sample from the 1000 hertz sampled data to achieve the 50 hertz rate. From this data. By using kind of downsampling, we want to make kind of 50 hertz rate data. So compute this and graph this and explain this. So I will deal with at the MATLAB situation. So let's just start to that. This is a kind of parameter setting, and this is 1000 hertz and the sampling time, and this is a time vector and the bin vector, and this is the kind of frequency, and this is the kind of lower target frequency, like where is it, like this. And this is the kind of downsampling process, which makes the our original 1000 data to 1000 data into this 50 hertz rate data. Anyway, and as we all have learned at the lecture, this is the kind of FFT process, and this is just a plotting process. So plotting process. Even though we resampled from the 1000 sampled data, still there is a kind of earliest frequency. So we I want to eliminate that. So before using a filter, we need to answer this. Explain conceptually why applying a digital LPF filter after the downsampling cannot recover the original signal cleanly. It's because when a signal is downsampled without the prior anti-aliasing filter, any high frequency component that exceed the new Nyquist frequency will fold back into the low frequency range. So once this folding occurs, the high frequency is mathematically mixed with the existing low frequency signal. So because the high frequency noise has disguised itself as a low frequency signal that falls within the passband of the low pass filter. So as a result, the filter will simply let it pass through. So from the question D, I will use the anti-aliasing filter. So this question is apply a digital low pass filter with an appropriate cutoff frequency to the first sample the data 1000 hertz sample the data signal before downsampling it to the 50 hertz, and then downsample the filtered signal data, filter the data, and plot this and verify that aliasing has been successfully prevented. So let's do that at the MATLAB 2. This one is a kind of low pass filter. Uh, Sorry, this is kind of low pass filter, and this is the filtering apply, and this is the kind of resampling process. And as I said, this is the kind of FFT process, and these are the just the make plotting process. So from the result, plot. Sorry, just a second. Ah, okay. So, from the result, I mean, before using a anti-aliasing filter, I mean, there is a kind of aliased frequency, but after using a anti-aliasing filter, I mean, same word with the low pass filter, there is there is no any more aliased frequency. So there is only, I mean, original frequency. We can clearly say, I mean, there is no aliased frequency. But I mean, as you see in here, I mean, it is a kind of broaden spectrum. I mean, we cannot say the which frequency it locates. So as observed in the graph, I mean, spectral leakage occurs because the observation time is limited to 1 second. So although the true frequency is 15.5 hertz, 15.5 hertz, the limited frequency resolution causes its energy to spread across the 15 hertz and 16 hertz beams. A common technique to mitigate this problem is zero padding. So, main question of E is the what is the underlying principle of zero padding, and does zero padding actually improve the true frequency resolution, and then just apply zero padding skill to my data and plot the resulting spectrum. So first answer to the what is the underlying principle of the zero padding is I mean simply saying zero padding is just where is it appending the sequence of the zeros to the end of the sampled time domain signal before computing the FFT process. So as a result, kind of this situation leads to the this acts as an interpolation in the frequency domain. It provides a smoother and higher density representation of the spectrum, allowing us to accurately identify the peak position and its true amplitude that originally fell between the discrete frequency bands. And also, for this question, I mean, zero padding does zero padding actually improve the resolution? Then this is not right, because I mean just adding the zeros to the data doesn't mean, I mean, we got the another new data, so there is no any resolution improvement. So this so apply the now it's time to apply the zero padding skill to my data. So I will deal with that in my FFT my MATLAB code, and my MATLAB code for the zero padding. Yeah, I mean, this is the kind of for the FFT situation, and this is the zero padding. This is a factor, and from the factor, I mean, there is a kind of broaden number of the data. So from the result, we can definitely say, I mean, much more smoother with the zero padding skill. So from the blue data, I mean, we can confidently say that 15.5 is our peak. But I mean, from the red, it is hard to say, I mean, 50.5 is our date. Okay, I mean, until here, I explained my problem. So, and thank you for listening my presentation.